again. So I thought what I'd do is I would go through yesterday's homework, or last day's homework, not yesterday, last day's homework, and give you what you should have. So you can again pause this and make your corrections as you go, or whatever. Anyway, for number 1, V equals delta E. Delta is a Greek letter that in our terminology means change in energy, divided by Q, which is a charge. And so V is in voltage, or volts. Energy is measured in joules, and coulombs is the measure for charge. So the definition, the actual definition is of a volt is that it is 1 joule per coulomb. That's how we define it. Okay. So looking at question 2, the figure on page 9 is the cells in series, and in page 10, figure 10, page 313, those are parallel. We actually talked about this, I think, last day, that a car battery, it looks like it's just one big giant battery, but it's actually got 6 2-volt cells that are in basically one giant container, but each cell is separate and separated by a complete wall. And so 6 times the 2 volts that each produces gives us an overall voltage of 12 volts. Okay. Number 4, diagramming the ammeter and the voltmeter. I pretty much copied what I saw in the textbook. So if you have an ammeter, has to be in series or in the line, as it were, in order for it to count the electrons as they go through. What I did with this one is I put an X and a Y just to make sense on my description. So you can see the X is right here and the Y is here. The electrons are flowing in this direction. So the voltmeter measures the difference between the voltage here and here. So whatever shows up on the meter itself is how far this fell. You know, if it was at one level and then went to another, that's what it measures. Okay? It doesn't do a mathematical calculation, it just senses it. Okay? So we're going to go out of it. Page over. Yeah, it didn't ask me. This question just asked for 3 electrical cells that are in parallel. So what is of interest to you, what you need to have, is basically this here, this part here. Whatever you have here, you could just have a wire that goes around, doesn't matter. If I even played with the idea of, why don't I put just a switch here? No. And I put a load here just because I was playing around. So, but this is the important part, right? Okay. So last question is that it turns out that the voltage of the three cells, if they're in parallel, is just the average. Okay. And I'm surprised in a way that we didn't mention this before, but it's the average. So if you have 3 1.5 volts cells in parallel, the overall voltage is 1.5. It doesn't raise it at all, but it's the average. The voltage of a series is the sum of all the voltages. Okay, one adds to another, making the whole thing higher. So now what we want to do is we want to look at the questions that are on page 314. It's actually question 9. So the first one is A has, now it doesn't matter, this thing has got the cells with the negative end coming out the top, doesn't really matter, but we notice there's 1, 2, 3, 4, there's 5 cells. It's 1, 2, 3, 4, 5. And so if we've got 5 cells times 1.5 volts each, that comes out to 9.0 volts. That's it there. Okay? Now what I want you to do, this B is a little bit harder. You have in series and in parallel, it's a combination. So I want you to pause right now and draw and then come back. Oh, positive, negative. Sorry, short one is always negative. Fat one or long one's always positive. So this is the positive end. This is the negative end. Okay? So do that one and come back. Okay, so the way to deal with these ones is to identify what they are, what each battery is, battery value is on its own. So each one of these cells in all of these cases is worth 2. So this guy total is going to be worth 4. This guy's going to be worth 4. And this guy's going to be worth 4. Okay? Now because this is the negative end, that means electrons are going to be flowing this direction here, this direction here, and down that way. Okay? Now, when we're talking about this parallel part, this part here, this is going to be whatever is coming out this end here is going to be the average of these two. So 4 plus 4 divided by 2 is going to be 4.0 volts going out here. This guy here is actually now in series with this entire group. It's as if we compress these together to give 4 volts. So this is going to be 4 volts plus these 4 volts. So total, let's change it. So 4.0 volts from the parallel plus the 4.0 from in series is equal to 8.0 volts. Okay? Okay, try the next one. Pause, try the next one, come back. Oh, that was C. I'm a dummy. That was C. B is down here. B. Okay, each one of these is 1.2 volts. So this part here is worth 2.4. This part here is worth 2.4 volts. So the voltage of this is going to be the average. So voltage is equal to 2.4 plus 2.4 divided by 2, 2.4 volts. Last but not least, D. Why do they do it in this order? No idea. Each cell is 1.5 volts. So voltage is equal to 1, 2, 3, 4. 4 times 1.5 volts. There we go. Okay. That's it. Okay. Onward. Onward. Okay. Before we start, just a little bit of conversation about resistance. Resistance really is pushback. Okay, and that can be on almost any level. But if we're talking about if we're talking about the physical world, you have blood vessels that go through your body, carrying blood to your working cells, and then the other blood vessels that carry the carbon dioxide and waste products back away from those cells. But because those are pipes, those things have a natural resistance, a natural pushback because of friction. Same thing is true with the plumbing in your house. You have pipes that carry water to your sink, and you have pipes that carry water away from your sink. And so because you've got liquid moving through those, there's a certain amount of resistance to that movement. It's between the friction between the liquid and the walls of your blood vessels and the walls of the pipes in your house. There's also a certain amount of resistance in rivers. When rivers are flowing downstream, there's resistance between the water and the substrate, the soils and the rocks. And you can see that if you're standing by the side of the water, by a river's edge, you'll see that sometimes turbulence occurs because of that resistance. In your digestive system, there's a certain amount of resistance of the food going through the different duodenum, the jejunum, ileum, and your large intestine. There's a certain amount of pushback. It doesn't flow all friction-free. And even we talk about resistance, we're thinking about rebellion in societies. Sometimes there'll be even a revolution where the government will be overthrown. So there's a pushback against the way that people felt that the country was being run, for example. And so there is this idea, resistance. Talking about electricity, electrons are moving. Okay? And it depends largely on what the circuit is made of. So electrical circuits also face resistance. We know that electrons are flowing through a conductor in a circuit. electrons are flowing through a conductor in the circuit. As you might expect, different substances provide different amounts of resistance to the flow of electrons. Different substances provide different amounts of resistance to the flow of electrons. Okay? And we've talked about this, in fact, in the past. If you have low resistance, that means the substance is a good conductor. And the example that we used was copper. If you have high resistance, what is it? What is that material called? Very good. It's called an insulator, right? And for example, plastic. Plastic doesn't. It's very high resistance. Okay. At the atomic level, this is talking about the flowing of electrons as they collide with atoms in a conductor as they go. Okay, so maybe later we'll draw. I don't have much room here. So resistance at the atomic level. At the atomic level refers to the flowing electrons. Boy, I really messed this up, didn't I? Flowing electrons that are involved in collisions with the atoms in the conductor. Okay? These collisions transform some of the electron energy into heat, and this is wasted. Okay, so these collisions transform some of the electron energy into heat. And this becomes wasted energy. Now, sometimes you want to have high resistance. For example, I don't know how many of you use hair dryers or curling irons. I know we have an electric stove. So anything that produces heat is actually designed to have high resistance at a certain point in the appliance. So let's look at a curling iron. The curling iron, the resistance in the cord that you plug into the wall is going to be low. That's good because it's made of copper. You want to get all the energy into the curling iron through the handle, and where it comes to the point that you're going to be using to clamp on your hair, that part is made of a different type of metal. It's made of a high resistance metal. I'm trying to think of the metals that is it NiCad, nickel cadmium. I can't remember what it is off the top of my head, but as the electrons go through there, it's such high resistance stuff that it causes the electrons to lose their energy. The electrons still go through, but the energy that each electron carries drops off a lot. So there's a huge voltage drop between the electrons coming in and the electrons going out, and all of that voltage drop results in energy of heat. Okay? So that's what that's all about. In 1827, Ohm's law. In 1827, George Simon Ohm discovered that the ratio of voltage to current was a constant. What does that mean? Well, it means that we can do some simple math and have some real fun. So the ratio of voltage to current was a constant for each particular conductor. This became known as Ohm's law. And resistance is measured in things we call ohms in his honor. And it is, we use the Greek letter omega. Omega is like this. So it's got this tail here, this loop, like so. Okay? And so basically this is the math equation that we use is this. Resistance. I'm going to do it over here. I'm going to show you something else. So this is Ohm's law. Resistance is equal to the ratio of the voltage to the current. Okay? Now, what I want you to do is I want you to, we're going to use we need to update our cheat sheet right away. We actually have two equations, one that we didn't do last day and one that we're doing today. So this is the magic triangle where resistance is equal to voltage divided by current. So voltage is measured in volts, current measured in amps, resistance is measured in ohms, like that. Okay, let's grab our cheat sheet. Here's my cheat sheet. So on the back, I'm going to do, from last day, we had the equation for what is a volt. Is equal to the change in energy in joules divided by charge in coulombs. I'm just going to put C. Okay? So this has a magic triangle. Volts is equal to so that if I give you any two of these, you can solve for the third. And I'm going to do a line here, and Ohm's law. Where resistance and ohms is equal to voltage, volts, divided by current in amps. And so I'm going to put it on my cheat sheet so that when I do homework, I can find it really quickly. So resistance ohms Oh, that should be, geez, I did that wrong. Should be an I. Okay, so let's do 2 examples. So it says a starter motor of a car is connected to a 12-volt battery. So here's V. If the starter motor has 75 amps of current, so that's current going through the car, what is the resistance of the starter motor? So resistance is equal to V over I, which is equal to 12 volts divided by 75 amps. Get my trusty calculator out. 12 divided by 75. Okay, turn it on first. That'd be good. 12 divided by 75. 0.16 is 0.16 ohms. Example 2. A flashlight using 2 1.5 volt cells. So you got to be careful. So this is the voltage, but I have to multiply it by 2. It's connected in series. Okay, so it's connected in series. The current, so current is 200 milliamps. So I have to now change that to amps. What is the resistance? Okay, so the first little, before I can start doing the actual calculation, voltage is going to be equal to 2 times 1.5 volts is equal to 3.0 volts. The current, now I'm changing from 280 to 280 from milliamps to amps. So that means I have to take this decimal and move it over 3 places. So 1, 2, 3. So it's going to be 0.280 amps. So resistance is equal to 3.0 volts divided by 0.280 amps. Clear screen. 3 divided by 0.28 equals 10.7. ohms. You okay with that? Easy peasy. The hard part is where you start is trying to understand what to do, and I really encourage you to do this. Okay? That way you can identify what goes where. Okay. So common conductors and their different resistances. So this is just kind of like give you a sense of resistance in things that we're familiar with on a daily basis. So if you've got 10 feet of copper wire, the resistance is quite small. It's only 0.1591 ohms. So small. 10 feet of aluminum wire has a resistance of 0.208. So that means that if I was to have hook both of these up to the same power source, this one's got a lower resistance, this one's got a higher resistance. and so you should expect that you're going to get more heat out of this one. Okay? 10 feet of steel wire has resistance of 1.0591, so almost 10 times the resistance of the copper wire, and so this is going to get quite hot. Human body, ooh, this is going to be interesting. The human body if it's dry is 500,000 ohms. If it's wet, much better conductor, 1,000 ohms. It goes down really far. And so this is the reason why we get severe burns if we connect with high voltage. We get severe burns. When we come in contact with high voltage. Okay, resistors. I wonder if I've got a picture of a resistor in here. I think I should have. Yeah, there's a picture. So resistors are not. We can already see it's not a bad thing because we use them in hair dryers and stuff like that. But even within more complex circuits, sometimes if the current is too much, we need to dial it back down, and so we're going to use resistors to do that. And these are just little teeny tiny components that have prescribed resistance to them. Some are large, some are small, and we use them to moderate current flow. Okay, so a resistor is used when the flow of electrons is just too high. In other words, you've got too much current. Current must be reduced so it will not overpower the load when we want to act on it. Okay? So some things would blow up if you have too much current going through them, so we dial it down. Okay? Let me see now. So we need to get this down. A resistor is used when the flow of electrons is just too high, i.e. too much current. So the current must be reduced. So it won't overpower the load. Okay, so I'm going to have a couple of videos in today's lesson that I'll get you to look at. Some of them are optional. There's one on what electrical burns to a person's arm, I think it is, and that's optional. You don't have to watch that. But there's another couple that probably be a good idea. Okay, resistors work much like a bottleneck. Which reduces the speed of traffic. If you ever try to get past an accident on Highway 97, you know what I mean. Yeah, two lanes have to go into one lane, that slows everything down. So it reduces the number of electrons that are flowing. It reduces the number of electrons that are flowing. More practically speaking, this means that the voltage and current are reduced in the circuit after going through a resistor. Means that the voltage and the current are reduced in the circuit after going through a resistor. So these diagrams are really hard to see even as we are here, but you'll see that there is an arrow right there. And so if you have both lanes open, there's low resistance, flow is easy. If you have an accident and you've got to reduce to one lane, notice that I made this smaller than this one. Okay, so this it reduces both flow and voltage, so current and voltage. Okay. Now, my suggestion is let's look at two things. Let's look at here's what I was referring to. These are three different resistors, and what you'll notice with them, these are very small. They're usually about the size. Here's a hairband. Okay, so a resistor is usually about the thickness of a hairband. Sometimes smaller than that, often smaller than that, as a matter of fact. But you'll also notice that on these resistors there are three, sometimes four different color bands. Okay, we're not looking at the yellows on the end, we're looking at the color bands in the middle. So these two are the same. Okay, this one looks, this one I think is the same, it's just been flipped around. So these all are three. Okay, so we're going to refer to that in a minute. Now, unfortunately, your notes are in black and white, which sucks, because these bands, these colors, have specific meanings. Okay, and because they're so small, it's impossible to write on them what they are used for without making so small that you can't read them. So they use colors instead. So this is how this works. So color code bands on resistors indicate the value. So color coded bands on a resistor indicate the value of resistance in ohms. Each band, or each color, represents a number. The first two bands represent the first two digits. The third band represents how many zeros you add. Sometimes there's four, and what they do is the fourth one, which is either gold or silver, down here, this is referring to the percentage of think it's percentage of variance or impedance or something like that, okay? So we don't worry about those. So if you had one, let's suppose we have a band, or here we have a resistor, and the first band, this is brown. So that one's brown. Oops. Let's say the second band, I'll color this in. Let's say this is black. And the third band, which is red. Okay. Now, so here we have the wires that are coming out the top, and wires that are coming out the bottom. So this is how you do this. Say brown is here. So the first digit is 1. The next one is black. So the next digit is 0. Okay? So those take up the first 2 digits. The third one tells you how many zeros. So I go to red and it says 2 zeros. So now I add the 2 zeros. So this would be a 1000 ohm resistor. Okay, does that make sense? Okay, now you can play with these things and come up with your own different combinations, and you may even have to do that in your homework. But right now I'm looking at the clock and saying that we've been chatting for 42 minutes. That's a long time. So I think I'm going to get you to do I know what I'm going to do. I would like you just to do on page 19, I only want you to do questions 1 and 2. And this should only take you a few minutes. And then the next day we're going to do the same thing that we did today. We're going to come back. We're going to try each one of these out. I'm going to get you to give it a shot. I'll maybe do the first one together. Do the next 3, giving you a shot at it, and then coming back and I'll solve it for you to make sure that you're good. But practice and practice, okay? And so next day we're going to start by doing that. Oh, you know what you could do too is on page 20. So I know, do these two. Number 1. Let's do number 1. Number 2 here, and then on page 20 do question number 9. And this will be kind of fun. This will be kind of like a little bit of a game. And then when we come back, we'll do the other questions. Okay? Okay. The score key is there for you for these if you need, and please do. Okay? Bless you. Thank you for a good day. You've been a very attentive class, I could tell, because only 3 of you fell asleep. So bless you, and I will see you next day. Bye now.